We consider now another example in which we try to see a flow field with no external forces occurring and try to find out the momentum flux and the unknown quantity for the given problem that we have. So we consider the example that water is being accelerated by a nozzle to an average speed of 20 meters per second and strike a stationary vertical plate at a rate of 10 kilograms per second with a normal velocity of 20 meters per second. So the conditions are that whatever speed with which the nozzle is generating 20 meters per second, the fluid strikes the plate in a normal direction with the same speed, 20 meters per second, and then after the strike, the water stream, of course, will splatter as it is expected in all directions, and the plane of the plate determine the force that is needed to prevent the plate from moving horizontally due to the water stream. So this is kind of saying that a plate, consider that the plane of my hand is the plane of the plate, and through a nozzle, through some pipe or some procedure, fluid is striking this. This will be, let's say, assume that a circular plate, but if we look at it, you will see only it's a small cross-section area, but the fluid is hitting it in the normal direction with a speed of 20 meters per second as has been given. And the question is that with whatever force the fluid is hitting this plate, we need to find out the force that is needed to prevent the plate from moving horizontally. That is, the plate should stay stationary wherever it is fixed. And this fluid motion, it will attack it with a pressure, with a certain force. The plate should be able to withstand that. And we need to find out that force which this plate should exert so that it can support the flow. So that is the question, and we look for a solution. The water jet strikes the vertical stationary plate in a normal direction. As I have just tried to show you, the force needed to hold the plate in place is to be determined. We of course assume that the flow of water at the nozzle outlet is steady. The water splatters in direction normal to the approach direction of the water jet. So they are mutually, in a way, perpendicular to each other. And you can see it from here. The picture is trying to indicate the same thing. Here is a nozzle and the fluid is moving in. And here is a plate that is fixed. So we can see only its a small cross-section area, but this plate can be rectangular or circular. Let us assume that it is circular. And the fluid, when it hits it in a normal direction, you can see that it is hitting it in a perpendicular direction. Then the fluid splatters all round in all directions. And the question is, we want to determine the force so that this plate should not move from its position, and it should stay there, and it should not in a horizontal direction. That is, the force of the fluid should not be able to disturb its fixed position. So that's the question. And well, the control volume as is being practiced is indicated by the red dotted line. The atmospheric pressure is, you can see, is being indicated as P atmosphere, and that is the atmospheric pressure all round. So it will be the same in all directions. So all the things that we need to see is the velocity that is coming in here. We need to know the velocity with which it moves in the normal direction or along the direction of the plate. And the rectangular coordinates that are being taken, as always, the horizontal direction is x-axis and the vertical direction is the z-axis. So we go into analysis of the plane of the problem or its a solution, and we see that the control volume I have shown you. We try to sum up all the forces, and the equation from the equation, the standard equation, we try to calculate the momentum flux. And the equation will be that the force that is being exerted will be equal to momentum difference at the outlet minus the inlet. So the momentum of the fluid with which it will hit the wall, and we want to calculate the force that withstands it. We try to see that if the velocity v1 in the x direction is denoted by v1 and the velocity at v2 in the x direction is 0 because it is not passing through the plate. The plate is a solid place. If there is any fluid moving, it's moving in this direction. The fluid here is not moving in this direction, and therefore V2 is 0 in the x direction. The resultant force, the reaction force, will be therefore equal to, at the outlet the V is 0, and therefore this is equal to the correction factor beta times the rate of change of momentum times the velocity v1, which is assumed to be uniform or steady. Substituting these values, we obtain that the force should be equal to 200 Newton. And again, by our same terminology or algebraic calculation that I mentioned in the earlier problem that we were discussing, this turns out to be, or this is equivalent to, about 20 kilogram mass. So you can see how this 20 kilogram mass is being calculated or computed. Again, the same equation, the Newton's equation. And if it is 200 Newton, the weight will be, or the mass will be, about 20 kilogram. So the value of Fr is 200 Newton. So the support must apply a 200 Newton horizontal support in the negative direction so that the force of the fluid is withstood by the plate and it is kept in place. And of course, the other things are rather trivial, and the result that the question that they wanted, we have arrived at the solution. They wanted to calculate, the question posed wanted us to calculate and find out the force that the plate should exert, should support, so that it is not displaced from its place. It stays fixed, and that has been determined as equal to 200 newtons, or almost just about 20 kilogram mass.